Hi, in this video, I'm going to go through the AQA AS level chemistry paper. It's paper one and it's from 2021. I'll do the first half in this video and complete the rest of the paper in the next video. Okay, first question about atomic structure. This is really just GCSE stuff, really. The model proposed by Rutherford is shown below. State two features of the current model that are not shown in the Rutherford model. Well, first of all, if we look at the nucleus there, we know that is made up of protons and neutrons now. And secondly, if you look at the electrons are not arranged in orbitals, and we know that they are energy levels, orbitals, whatever. They're the two things I'd go for there. Okay. A sample of tin is analyzed in a time-of-flight mass spectrometer. The sample is ionized by electron impact to form +1 ions. Okay. There's the data, the MZ value, and the abundance. Give the symbol, including the mass number, of the ion that reaches the detector first. Okay, now the one that reaches the detector first is going to be the lightest one, because they've all got the same kinetic energy, remember? So kinetic energy is half mv squared. So the smallest mass, it means you're going to be going for fastest. So that's going to be the 112 isotope. So we have to write down SR 112, and it is an ion. It's a positively charged ion. So we've got to put that there as well. Okay, calculate the relative atomic mass of the tin in this sample. Okay. Give that to one decimal place. Well, first of all, we've got to work out the percentage of the 120. So we just subtract all those abundances from 100, and we work out there that that means that the abundance of the 120 is 30.84%. Now, it's a pretty just straightforward to work out the relative atomic mass. So the relative atomic mass, what we've got to do, of course, is multiply the mass of each ion, so there's 112, multiplied by its abundance. Now, instead of using a percentage, so we don't have to divide by 100, it's best to just give that as a decimal. Okay. And then 114 multiplied by 1178 plus the mass of 117 multiplied by its abundance, 0.3497, plus the 120, which is 0.3084. Right, this is quite an easy question for an AS paper, really, because normally what they, of course, they do is they give you AR, and then one of the abundances is missing, and you've got to find that was just the straightforward of. So just put those numbers into a calculator. What you get is 116.451. It says give it to one decimal place, so we should write down our answer as 116 point, round that 4 to 5. That. Okay, right. So question about magnesium, its compounds. So you have to know some more stuff for this question. One observation where magnesium reacts with steam, and giving the equation for that. Right, magnesium reacts differently than all the other group 2 metals. It won't react with cold water, but it will react with steam. And you don't get the hydroxide like you do with all the other ones. You get, I'll give state symbols here. You don't get the hydroxide, you get the oxide. Magnesium oxide, which is a solid, and you get hydrogen gas. Give an observation. I would say it glows with a bright white light. The other thing you could say is this silvery metal turns into a white powder. This magnesium oxide is a white powder. Okay, describe the bonding in magnesium. Well, bonding in magnesium, of course, is metallic bonding. So what have we got here? We're going to have I wouldn't draw a diagram, it's only 2 marks, so I'm just going to draw this. So these are magnesium ions in a regular lattice, yeah, and in between them, you've got delocalized electrons. Okay, so what I would say, what would we say here? So regular arrangement of positive ions. And a sea of delocalized electrons. And it's the attraction between the positive ions and the negative electrons that hold the whole thing together. 2 marks, that's plenty there. Again, that's not really that much further on than GCSE, that question there. Okay, 2.3, in terms of structure and bonding, why magnesium chloride has a high melting point? Well, it's an ionic structure, an ionic lattice. Let's get that word lattice in there, as or giant ionic lattice. And you've got strong attraction, electrostatic attraction, let's say, between the Mg2 plus ions, the positive Mg2 plus ions, and negative Cl minus ions. I would, if you know the charges on those ions, write them down. And it's always worthwhile saying in these questions, the mark scheme quite often says something like you need a lot of energy to overcome these attractions. So the melting point is going to be high. Okay, one used for magnesium hydroxide, Mg magnesium hydroxide is not asking for the formula, I'm going to write it down anyway. It's insoluble, and so that's used as an antacid for indigestion, neutralizes stomach acid. Well, because it's insoluble, of course, it doesn't make the stomach alkaline, which you couldn't have. Okay, the OH minus ions don't dissolve. Okay, this question is about redox reactions. State in terms of electrons the meaning of an oxidizing agent. Well, an oxidizing agent oxidizes something else, and don't forget oil rig. Oxidation is loss, reduction is gain. So oxidizing agents take away electrons from other things. Right, 3.2, we have got a redox reaction. So we've got this, the dichromate ion, which you might be familiar with from the organic chemistry. The dichromate ion can oxidize. That's either called sulfite or sulfate 4 ion. It will oxidize it to sulfate ions, and the dichromate gets reduced to chromium 3 plus ions. Okay, so we've got to deduce 2 half equations and then combine them to write the full equation. Let's do the sulfite one first. Okay, so we've got SO3 2 minus, and that goes to SO4 2 minus. Right, so the first thing is to balance for oxygens. We've got 3 oxygens on the left and 4 on the right, so we need to balance that by balance oxygens by putting water in, of course. Now we need to balance for hydrogens by putting H plus ions. We've got 2 hydrogens on the left and 1 on the right, so we want 2 there. Now we have to balance for charges by putting electrons in. So we have a total of -2 on the right. And on the left, we have got an overall charge of -2 plus 2, 0. So we need another 2 electrons there to make it -2 on the right. Okay, so you can see the sulfite has been oxidized, the sulfate, it's lost 2 electrons. Right, let's do the dichromate one. Okay, so we're going to have the dichromate ion, and that gets reduced to the chromium 3 plus ion. Now you have to be a little bit careful there, because you have to remember to put a 2 there, okay, to balance the chromium first of all. Now we balance for the oxygens. We've got 7 on the left, so that means we need 7 waters on the right. Next step, balance for hydrogens by adding H plus ions. So we need to add, we've got 14 hydrogens on the right, none on the left, so we want 14 here. Now let's be a bit careful about balancing the charges here. Now we've got to add electrons somewhere. Let's see, on the left-hand side of the equation, we've got 2 minus from the dichromate and 14 pluses there. That makes plus 12. And on the right, we've got 2 lots of Cr3 plus, so that's only plus 6. So that means we would need 6 electrons to balance that on it. So 6 electrons here. Now we've got to combine those two half equations. Well, the green one is only 2 electrons and the blue one is 6. So we're going to have to multiply this one by 3 before we add them together. So let's now do that. So we're going to have 3 sulfites, 3 waters, 1 dichromate, 14H plus. The electrons are going to cancel out, so I'm not putting those in. And then we're going to have 3 sulfate. So I put 4 there, should be 3. 3 sulfates. 6 H pluses. And then we're going to have 2 chromiums and 7 waters. Now we can see we need to simplify that because we've got waters on both sides of the equation. We've got 3 there, we've got 7 there. So that means we get rid of these ones. Take 3 from both sides of the equation. So that 7 becomes a 4. And we can do the same for some of the H pluses. We have got 14 here and 6 there. So take away 6 H pluses from both sides, get rid of them. 14 minus 6, that gives us 8 H pluses here. That is our balanced equation. Okay, right, now this is one about testing for ions, unknown ions in aqueous solution. So before we answer the questions, let's just see what's going on here. So test 1, they are adding sulfuric acid. Okay, now if you get a white precipitate, this is, so when you add sulfuric acid, that is probably because solution A contains Ba2 plus ions, barium ions, okay, and you're forming insoluble barium sulfate. That's the white precipitate. So that's a test for barium ions. You add sulfate ions if you get a white precipitate. When you add sulfuric acid to B, you're getting effervescence. Right now, that probably means that you've got carbonate ions in B, and that's making carbon dioxide gas when you add any acid to it, in this case, sulfuric acid. And C, no visible change, so nothing there. Now, adding NaOH. Okay, now what we can see here, this tells us there's A and C, nothing happens, but in B, you get a gas that turns litmus blue, so an alkaline gas, and so that's got to be ammonia. So that means what have we got in there? We have got NH4 ammonium ions, okay? That's the positively charged ion in B. So B, we can tell straight away now, is ammonium carbonate, because we know the positive ion and the negative ion. Okay, let's have a look at the test 3. Now, acidified silver nitrate, that is a test for halide ions. And here, see, we're getting off-white precipitate. So that could be due to the presence of chloride ions or perhaps bromide ions. Chloride ions usually, silver chloride is white, and silver bromide is usually described as being cream. So it could be either of those two. A, nothing happens. We've got to say anything there. And B, we're getting effervescence. Now, why are we getting effervescence? It's because this is acidified, and all that tells us really is that we have got carbonate ions, which we knew already, because when you add sulfuric acid to it, you get effervescence there. Okay, so we know what B is, ammonium carbonate. We don't really know what A is. It's a barium salt. We don't know what the negative ion is. And with C, again, we don't know what the positive ion is there, but we do know it's probably a chloride or a bromide. All right, let's answer the questions now then. So suggest the identity of the positive ion in solution A. Well, we said that's barium, isn't it? You could conceivably say strontium as well, because that strontium sulfate isn't very soluble, but I'm going to say barium. And write a simplest ionic equation for the formation of the white precipitate. Well, that's going to be Ba2 plus, and that reacts with sulfate ions in solution to form a precipitate of barium sulfate. So we don't write it as separate ions because it's a precipitate, and state symbol there, S. Right, different gases are formed when solution B reacts in tests 1 and 2, okay? So solution B, we remind ourselves, is ammonium carbonate. So ammonium carbonate is going to be NH4, and we're going to need 2 of those because there's only a 1 plus. We know what B is. Right. Suggest the identity of each gas. Well, we said when we had the sulfuric acid here, that's going to react with any carbonate to form carbon dioxide. I said before, when you add alkali and you get ammonia gas given off, yeah, you'll get you've got ammonium ions present. Get that. The ionic equation for the formation of the gas in test 2. So that's the ammonium. So let's do that. So we start off with NH4 plus. That's the ion. React that with sodium hydroxide. It's only the OH minus ion that's doing it. I think the sodium is a spectator ion. Right, the OH minus is going to act as a base and remove an H plus from this. So it's going to leave behind NH3. And it's going to form water. Maybe put state symbols in there, AQ, gas, liquid. Okay. Right, the students thinks that solution C contains either chloride or bromide ions. Now remember why that was, because if it was chloride we formed the white precipitate, it could be AgCl, which is white, or it could have been that the off-white precipitate was silver bromide. Not quite sure. How could the student confirm what test are going to do? Right, do you remember if you add dilute ammonia, it's got to be dilute ammonia solution. That will redissolve silver chloride precipitate. So the silver, if you add ammonia, if it's silver chloride, it will dissolve. If it's silver bromide, it won't dissolve. So that's how you distinguish if it's chloride or bromide ions. It's important not to use conch ammonia there, of course, because conch ammonia will also dissolve still silver bromide. You probably remember it. Conch ammonia doesn't dissolve silver iodide. Yeah. Right, chlorine then. So you need to know your. All right, okay. We actually use water later on. Right, the question is chlorine has a low boiling point because the forces between the molecules are weak. Right, what kind of, so chlorine molecules, what are they? They are Cl2. So obviously we haven't got any permanent dipoles there because the electronegativity of the chlorines are the same. So we're talking about van der Waals forces. Okay, now how do they arise? Well, van der Waals forces, you get a temporary dipole due to the random fluctuations in the electron cloud. Okay, now if you've got a temporary dipole, that then induces dipoles in neighboring molecules. And the what the forces of attraction between the molecules is the attraction between the temporary dipoles. Okay, so that is that question done. Right. Right, 5.2, give an equation for the reaction of chlorine with water. Okay, and right, so how does chlorine react with water? We get Cl2. You get a disproportionation reaction, do you remember? So one of the chlorines gets oxidized to chloric 1 acid, HCl, and one of them gets reduced to the chloride ion in HCl. Okay, that's the equation. Why is it added to drinking water? It is to kill microbes. Right. Chlorine reacts with cold aqueous sodium hydroxide in the manufacture of bleach. Right. Given an equation for this reaction, again, this is another disproportionation reaction. So we've got chlorine and sodium hydroxide. One of the chlorine atoms gets reduced to the chloride ion, sodium chloride, and one gets oxidized up to the chlorate 1 ion, ClO, NaClO. The sodiums are just spectator ions there. We're going to have to balance that by putting a 2 in there, and you can probably see that you're also going to make a molecule of water. Okay, so you've got to know that equation. Okay. Right. Calcium sulfide reacts with calcium sulfate, as shown below. So it gives the masses of the two things reacting. And first of all, we have to show that the calcium sulfate is the limiting reagent. Okay, so how are we going to do that? We need to work out the moles of each of those things, okay? So let's do the moles of the calcium sulfate first. Sulfide, sorry. That's going to be mass divided by the MR. We've got 2.5 grams of that. The MR, they tell us, is 72.2. So that is going to be 0.0346 moles, okay? Now we can see from the equation that 1 mole of calcium sulfate can react with 3 moles of, 1 of calcium sulfide can react with 3 of calcium sulfate. So that means that this is enough to react with. This will react with 3 times 0.0346 moles of calcium sulfate. Work that out. 3 times that is 0.1039. Right, now we've got to show that calcium sulfate is the limiting reagent. So let's work out the moles of calcium sulfate, and it should be less than that value there. So let's work out the moles of calcium sulfate by doing mass over MR. Moles calcium sulfate, mass over MR. The mass we have got of that is 9.85 divided by its MR, 136.2. That gives us 0.0723 moles. Okay, now you can see there, look how many moles of this we've got. We've only got 0.0723, whereas the amount of calcium sulfide we've got can react with that amount of moles, which is bigger. So therefore, the calcium sulfate is limiting. Now, what we've got to do now is we've got to calculate the mass of sulfur dioxide formed, okay? You've got to remember here, it's the moles of calcium sulfate is limiting. So, let's see, moles of calcium sulfate that react is all of this, yeah? 0.0723. Now we look at the equation here, we've got a bit of an awkward ratio here, because we can see here, 3 moles of calcium sulfate will give us 4 moles of SO2. Okay, let's write that down. 3 moles calcium sulfate give 4 moles of SO2. So therefore, that 0.723 moles of calcium sulfate, that will give 4/3 multiplied by 0.0723 moles of SO2. Right, we calculate that 4/3 times 0.0723. That gives us 0.0964 moles of SO2. We need to work out the mass of SO2. So moles, mass of SO2 is equal to the moles multiplied by the MR. They don't give us the MR of SO2, so we've got to work that out. MR of SO2, 32.1 for the sulfur, 2 times 16 for the oxygens. That gives us 64.1. So that's going to be equal to 0.0964 multiplied by 64.1. That gives us 6.18 grams. There's our answer. Okay. That's question 7. All right, this question is about combustion. State the meaning of the term standard enthalpy of combustion. So, okay, it's the enthalpy change when 1 mole is combusted completely in excess oxygen, right, at 298 Kelvin. Okay, or sorry, all reactants and products in the standard states at the temperature stated and 100 kilopascals pressure. Okay, so it's worthwhile for those definitions. They've kind of like changed slightly over the years, so it's worthwhile looking in the mark scheme for the latest correct version, or the version they like the best at the moment. Right, 7.2. So a student does a calorimetry experiment here to determine the combustion of propan-1-ol. Okay, so what are we going to do here? You can see we're going to need the following, to do the following up. We're going to have to work out the quantity of heat released. Q is equal to MC delta T. And then to work out delta H, we have to then use this equation. Delta H is equal to Q divided by the number of moles of propanol that we've burnt. Okay, so we're going to use both of those. And if people don't really know what they're doing, they just do the blue equation and leave that as the answer. That's not the answer. That's Q, the quantity of heat released in the experiment. It's not the quantity of heat released per mole. So you've got to use the green equation. Right. Let's work out Q then. So Q, now M is the mass of the water here. And that's another common mistake. It's not the mass of the propanol. It's how much water you're heating up. So it's not that. It's 150 grams of water. The specific heat capacity of water is 4.18. That's C. And delta T, let's work out delta T. Well, the final temperature is 35.1 and the starting temperature was 21.2. So we do that, we get delta T is equal to 13.9 Celsius, degrees Celsius, 13.9. Do that on our calculator, we get a value of 8,715.3 joules. Okay, it's joules there, not kilojoules, because look, that's per unit there. Okay. Right, now we have to work out, use the green equation, we have to work out divide Q by the number of moles. So first of all, we need to work out the moles of propanol. The moles of propanol is equal to the mass over the MR. Okay, so the mass of the propanol was 0.497 grams. And the MR propanol, they tell us, is 60. So that is equal to 8.283 times 10 to the minus 3. Okay, so delta H is equal to Q over the moles. Q 8715.3. And the number of moles is 8.283 times 10 to the minus 3. Work that out. We get a value of 1.052 times 10 to the 6 joules. Let's convert that to kilojoules, divide by 1,000. We get 1052 kilojoules per mole, I should say, yeah. Right, now you have to be really careful there. If I would lose, I'd only get 2 marks out of 3 there, because I need to remember this is exothermic. So we need to state that delta HC is minus 105, and I'm not going to put in the 2, and I'm going to put that there because that's the 3 significant figures, but you wouldn't lose a mark for that probably, but you definitely lose a mark for forgetting the minus, and that's a very, after doing all that work, you only get 2 out of 3 marks for a tiny little mistake at the end, so be careful. That's the answer. The enthalpy of combustion determined experiment is less exothermic. And of course, the main reason for that is the one they say is heat loss. You've got to give another reason. And the other reason I would always give is maybe have some incomplete combustion. In other words, you're going to make, instead of carbon dioxide, you might get some carbon monoxide and some carbon solid forms. You're not going to get as much heat energy released. Okay, here is a big titration question, 6 marks then. Okay, so draw a little diagram there, which we'll talk about in a minute. Right, okay, a student is provided with 5.6 grams of ethanoic acid, and it's contaminated with sodium ethanoate. Okay, dissolves that and makes up to 200. So look there, that's what I've done there. In a volumetric, be careful there, because normally when you use a volumetric, it's 250, not usually 200. So you have to be careful with that in the calculation. Okay, then it takes, the student takes 25 of the solution out into a conical flask there and titrates against sodium hydroxide, solution of 0.35 moles per decimeter cubed. And I've written down the value of the average titer there, which we haven't worked out yet, but okay. Now, first bit, use the results to calculate the mean titer value. So we've got to use only concordant ones. And you can see that the only 2 concordant ones, they've got to be within 0.1 of each other, are that one and that one. Okay, this one is not within 0.1 of it, and obviously this one is way too big. So the average of those two is 20.275 centimeters cubed. Okay, so that's what I've written up there. Right. Okay, so how use the mean titer to calculate the percentage biomass of sodium ethanoate in the original sample. Right, what I should do here is write down the equation for the reaction. Okay, so they haven't given us that. So ethanoic acid is that, and it's going to react with NaOH. The only important thing we really need to worry about is it's a 1-to-1 ratio. So we've got and H2O. So 1 mole of sodium hydroxide reacts with 1 mole of that. That's the only thing we really need to worry about from the equation there. So what we're going to do first, well, the first thing we can do is we can work out our moles of NaOH. So let's do that. And we can work that out by, because you know, the concentration times by the volume. That's 0.35 multiplied by 22.75. Now we need to convert that to dm cubed to divide it by 1,000. So the moles of NaOH then are 7.096 times 10 to the minus 3. Right, from our 1-to-1 ratio, then we can say here that we know 1 mole of ethanoic reacts with 1 mole of NaOH. So we can say the moles of the ethanoic acid and don't forget that came from 25 centimeters cubed. So in 25 centimeters cubed is 7.096 times 10 to the minus 3. So therefore the moles ethanoic acid in total in the 200 well, 25 goes into 200 8 times, so you need to multiply that by 8. So 7.09 times 10 to the minus 3 multiplied by 8 gives us 0.0567 moles. We need to work out the percentage by mass of sodium ethanoate. Okay, that's what we need to do in the original sample. So we need to work out the mass of ethanoic acid there. So how would we do that? We do moles times MR. The MR of ethanoic acid, that's ethanoic acid, is equal to 60. Let's do that. So here's the mass of ethanoic acid. Moles times MR, 0.05677 multiplied by 60 is equal to 3.406 grams of ethanoic acid. Right, now if we look at our, it tells us here that the original mass was 5.6 grams. Okay, of that, 3.462 is ethanoic acid. So we need to work out how much of the impurity, the sodium ethanoate, we've got in there. So let's do mass of ethanoate. That's going to be the total mass, 5.6, minus the mass of the ethanoic acid, that's 0.4062. That gives us 2.19 grams. Okay, now it's not the mass though, we want the percentage mass. Okay, so finally we've got to do, I'm running out of space there, percentage mass is going to be 2.19, that's the mass we've got, over the total mass, which is 5.6, multiplied by 100. That gives us 39.2%. Okay. Right, last question here. I think this is about halfway through the paper, so I'm going to stop after this question. The student rinses the burette with deionized water before filling with sodium hydroxide. Explain the effect this will have on the value of the titer. Well, if there's a little bit deionized water left, that's going to dilute the NaOH. So that means that you get the titer will be bigger. Of course, you shouldn't do that when you do the titration. You should rinse the burette with deionized water, distilled water, and then you should rinse it with the solution that you're going to use to get rid of any traces of the distilled water, which will dilute the stuff you're going to put in there. Okay, so that is halfway through the paper, so I'll continue that in the next video.